We're going to draw up some wiring schematics and use all this stuff here to build this thing. In the process, I'll probably light something on fire. We'll go through how to read the schematics, what not to do, and how to troubleshoot. It's a pretty common industrial process. If you watch this video through the end, you'll definitely gain some knowledge. Wiring schematics are not that difficult, and I'm going to walk you through them. And run these wires. Ow! Shit, that hurt. Alright, so we're going to be making a level controlled water tank. As you can imagine, it's pretty common in industrial settings. It's a symbol for a three-phase circuit breaker. Why do I have a three-phase circuit breaker? I don't know. That's just what I got. So we're going to plug that into the panel. We're only going to be using 120 volts. So on our schematic, this whole line right here is going to be our feed. Anything that's attached to here electrically is the same point. And then you're going to go through, a series of permissives and then a load. Usually it's a circle that's going to consume the voltage. And then we'll have our neutral over here. That's how, schematics work. Those are my two loads. Sometimes it's easy to just start with that. Industrial schematics, you're going to see dozens, if not dozens, maybe hundreds of loads. It's easy to just remember. Every load is like a separate, it's a separate idea. So if you see this and this, you might as well just not even look at this. You want to look at pump one, and you're only looking at whatever's attached to pump one as your first tip. There are neutrals over here. And this neutral is going to tie to ground. 120 neutral, aka like the minus side, or where the power goes. You got 120 volts here, 0 volts here, 120 volts here, 0 volts here. And we're just going to draw a little puzzle to see if we can get to relay 1 and to pump 1. So the first part of the schematic, I have a normally open float switch. Meaning when that float switch going to be sitting in the water, and when the water level comes up high enough, it's going to hit that float, and it's going to close that circuit, and it's going to turn on relay 1. So we'll start with that, and then I'll demonstrate. You could go the float switch right to pump 1, but that's probably not wise because these float switch wires are really small, and the amount of power that the pump consumes, the amperage, would most likely melt the wires. So I'll go ahead and demonstrate that for you guys now. All right, so I attempted to make this little battery pack and run these wires. Ow! Shit, that hurt. Something's hot in there. Holy crud. Anyways, I attempted to make this little battery pack and short these wires together. Something got really hot. I don't know where it is, but maybe these wires already melted inside of there. Something's shorting out right here. You guys are going to get me in trouble. It's a really lame demonstration. But, yeah, I'll create an electrical fire in my panel later. That'll be more fun. But, yeah, I tried. I don't know. Alright, so instead of lighting something on fire electrically, I'm going straight hot to this terminal here. Terminal to ground. Shorted 120 to ground and it blew up. That was 12 volts. Imagine 120. I got a baby and a wife in the apartment. I can't afford to have an explosion. Thanks for watching. Okay, so up to this point I've wired in my float. Pull this schematic up to show you guys. Circuit breaker through a fuse to a float. We're going to verify that it's a normally open float here in a second. And then we're just going to run that over to relay 1. Relay 1 is one of our loads. So in other words, it's a device, it's an output. It's something that we turn on and off. The way that relays work is you turn the relay on and off, and it has sets of contacts. Think of like a light switch. You flip a light switch, and that's like turning a relay on, and then it's going to either close or open sets of what we call contacts. If you can see this, 13 and 14, that's the coil. You always want to verify you got 120 volt AC coil. So we're going to run our hot to 13 and our neutral to 14, and that's going to be our first load. Let me wire this up and then we'll demonstrate it. Okay, so we got a longer wire. I'm running it down to A1 again, which is always the hot on the coil of your relay. So run my A2 to this point right here. This is what I'm using for my neutrals. All right, so I got my circuit breaker, then fuse, then float switch, running around here through my relay, then A2 down to neutral. And back to, in this case, it's going to go to an outlet in the wall, which is going to go to a main circuit breaker, which has a ground in there. The neutral and the ground will bond together inside of that circuit breaker. In order to verify that I got the hot and neutral correct, what I'm going to do is I'm going to pull out this relay and use this device. It's a tick tracer, and I'm going to make sure that this side of the circuit is hot and this side is neutral. The reason I have to do that is because I'm just using a random extension cord, and I'm not 100% sure that I have the right side. Usually the neutral has like an extra line on the insulation, but just to be sure, I'm going to do it this way to remain safe. So we got power coming in here, through here, down this wire. Come on. Oh, circuit breaker's off. Circuit breaker's on. Look at that. Power is coming down here to my fuse. Looks like I used a good fuse. Power is going through there, 120 volts to there. Then right there is my float switch. So let's check that out. So it's coming in on this line here, and it's coming out this line. Look at this diagram. You see the problem? This float switch is supposed to be normally open. It's supposed to be interrupted until it flips. Well, there's an easy fix for that. I don't remember exactly how to do it. Oh yeah, I just flipped that thing over, I think. Yeah, that's how you do it. These float switches were like crazy, like $1 or something. All right, so this should be normally open now. Yep, so you go there, then no power coming out. Flip the float switch, power goes through. So normal state is open, flip it over, close. All right, so I plugged in my relay, and when I flip this, the relay should click. But it's not. Aha. Oh, I have a bad connection right here. Look at that. There's a little troubleshooting tip for you. So you got your 120 going to your relay. It's actually going through that coil. So you still have voltage coming out of it, but the power is not being consumed. There's zero current on this line. Once I make this connection to neutral better, like get a good connection, you'll have voltage going in, no voltage going out, and you'll actually have power running through that line. So what I'm going to do is I'm going to turn off the power so I can safely do it, and I'm going to make that connection better right there. I did not do that on purpose. It just happened that way. All right, people. Now we're going hot. You see the kind of equipment I'm working with. I'm a little bit leery plugging it in, and I'm flipping the float switch. Do you hear that relay clicking? Do you see the indicator changing? So we have an operational relay that's run by a normally open float switch. Next. So I want to run pump 1. I want to run the power through one of the contacts in relay 1. So what I'm going to do is, I'm going to steal power from over here. I'm going to pull it from a point that's always hot. And then I'm going to run through one of the normally open contacts on relay 1. And I'm going to power the pump that way. So out normal state open. So out of the box, when relay 1 is not energized, there's going to be nothing here. When you turn on relay 1, that 120 is going to pass through there to pump 1. Again, I'm doing it through the relay contacts because I don't want to run all the power that I'm consuming in the pump through these float switches. I could just go float switch right to pump 1, but I mean, that's really thin wire. Realistically, it would probably work, but I'm showing you guys what they do in the industry. You run power, like motors and pumps. You either run them through relays if they're really small motors, but usually what you do is you run it through a contactor or a starter. But on this one, we're just going to run it through a relay. A lot of stuff gets, smaller loads get run through relays generally. So let's wire that up real quick and then I'll show you the lift station. There's more things that can be improved and we'll go through them after that. All right, so I got my 120 volts for the common side of my contact on my relay. In other words, this is the power that's going to be feeding my pump through the relay contact. I pulled it off the bottom side of the fuse, just as we used in the schematics. I terminated it right here. I think that's point 12. Yep, on point 12. Right there. My hands are dirty from my job, by the way. People, don't judge me. Right there on point 12. And we want to go to the normally open. So we're going to go to terminal 8. Terminal 4 would be the normally closed point. So when you plug it in, it would be energized. And then when you energize, like terminal 4 would be energized without the relay on. And then when you turn the relay on, this little guy is going to go over that way. Okay, I got everything wired up. Is it pretty? No. Is it going to work? Maybe. I got my pump here. Actually, I got everything wired up. What I'm going to do is I'm going to turn it on right now. I'm going to do this really safe. So what I'm going to do is I'm going to turn on this circuit breaker in the panel, knowing that the feed coming in is dead. I'm going to walk away and plug this in. And nothing blew up, so we're safe. I'm gonna move my camera and show you guys what we got. Okay, people. Welcome to the future. Tick tracer, all right. Just to show you guys that we are legit. Yeah, that thing was supposed to beep. All right. So I got my tank. That's the... Thing's too sensitive. This one right here. I gotta hold that right there. Actually, I'm not gonna do it because it's not safe. I'm pouring water next to a panel. I don't want to touch it. It's not really grounded. We're not doing that. I did tell you guys I was gonna light something on fire. Still figuring out how to do that. It might happen right now. Let's see what happens. So what happened at this moment was an absolute tragedy. What happened is my microphone died. What also happened is I slowly poured this water into this pump station. It turned on for just a second or two. It would pump a little bit of juice out and then it would turn off. Then a couple seconds later it would turn on for 1 or 2 seconds and then it would turn off again. The reason being is that we're just using a single float switch to control our process. It's a momentary float switch. You can see it pumping up and stopping, and then again it's going to pump for a second and stop. No bueno. What are we going to do to fix the problem? I'm sure I'm explaining it better right now. I look like I'm really into it, but that's okay. We're going to make do with what we got. So what we're going to do is we're going to seal in relay 1 with itself. So that's going to be a set of normally open contacts on relay 1. So relay 1 is not on, so we're not going to turn on there. But once this float switch hits, relay 1 turns on and its contacts turn on, and that is going to seal it in. So as soon as it turns on, it's going to stay on. Even if this float switch opens up, we're still going to get voltage going through those relay contacts I don't know who came first, the chicken or the egg. I don't know. That's just the way it works. Seal-in circuits, they're everywhere in industrial processes. You definitely need to understand them to be any good. It's like one of the most important things, seal-in circuit. So when relay 1 turns on, this circuit's going to become active. But we don't want it to just stay on forever. We need something to interrupt it. So we're going to put another float switch even lower in the tank. And when that float switch drops down, it's going to open up the circuit. So we're going to have another normally open. Ignore that. I don't have a magic marker eraser. We're going to have another normally open float switch. We'll call that the low float. So that thing's going to be hanging out towards the bottom of our tank, you know. So when the high float turns on, this one's going to stay active most of the time because it's near the bottom of the tank. This one's going to turn on. It's going to energize relay 1. We're going to seal in here. And once that low float is hanging, then we're going to interrupt the circuit. That's how I'm going to run this. Let's wire it up. If I made a mistake in my logic, we're about to find out. So this set of contacts on the relay, if you remember we were talking, there's like 4 different sets of contacts. We could use a different set of contacts. We probably should, but I'm just going to use the same one. I'm going to reuse this point right here as this point because technically speaking, electrically, this is all the same circuit. So we're just going to reuse that same set of relay 1 normally open contacts. And where I have that wire coming out to feed that pump, I'm also just going to run that up here on the output side of that first float. If that was confusing, I'm sorry. Another way to do it would be I could go to that terminal. Actually, yeah, let me just do it that way to make it less confusing for you guys. Where the terminals are for the floats, I'm going to pull out 2. I'm going to terminate a wire here and a wire here, and I'm going to run it set through a different set of normally open contacts on the relay. So let me do that now. 9 and 5. It's going to come in on 9. Normally open terminal is 5. That's what we're going to do. All right, so I landed my 2 wires on either side of that float switch to create a parallel circuit to that float switch. This set of contacts is just a parallel to that. You can always think or that's just a parallel branch right there, boom. FYI, PLC logic, if you can read this, you can read PLC logic. There's just some other functions in there that you have to learn. Most of them aren't that complicated. It's actually a lot easier than you would think. If you've never done it, it's pretty straightforward. So we're going to go 9, 5, and it really doesn't matter. It's just like an on-off switch. I mean, if you were using, you know, if you're using the normally open and the normally closed, then you do need to, you know, the polarity and which terminal goes to where is important on the relay. So we'll do it the right way. So the incoming side is going to go to the common relay contact, which is 9. This one's going to 5. Again, I know this isn't clean. I really hope that, you know, it's, yeah, you know, I hope this video is like cool or seems interesting or seems fun. If you would enjoy doing this, like as a hobby, this is what I do at work pretty much every day. It's not always this though, it's always different stuff. Sometimes you have to log into PLC logic and be like, okay, why does this machine keep turning off? Sometimes you're calibrating stuff. Sometimes you're just helping people figure out, you know, why something isn't working. But it's basically a bunch of stuff just like this, but like hundreds and hundreds of things like this with, you know, this is very rudimentary, but also is some more high-tech stuff all intertwined. And a lot of it seems a little intimidating when you first look at it, but it's just 150 or 500 things like this all integrated together. It's really not that crazy if you know, start to get some practice or whatever. Okay, anyway, so we got it. So I got a parallel John on this, and yeah, if I plug this in, this is just going to keep running. I'm going to flip the float switch. This is going to latch in. It's just going to keep running. So we got to figure out a way to, you know, interrupt this circuit, put another low float, and then go back to the original circuit. So I'm going to do that now. All right. So I took off the wire that feeds the relay. I moved over one terminal. And again, we just said we're going to interject this float switch in series. So after that parallel circuit, it's going to come out. It's going to go through this float switch back over here and back to the relay. And that's that. I'm going to wire that up and we're going to test it. Installed our parallel latching relay contact, and we installed a low level switch, normally open. So it's going to hang down here and it's going to be made. It's going to be a closed circuit. So basically we don't even have to worry about it. But once the tank gets low, it's going to interrupt the circuit and the cycle is going to start again. I just wired it up. I didn't test anything. So we'll see if it works. Oh, I did test the low level switch to make sure it was normally open. All right, so here's a good thing. So I'm turning on the circuit breaker. I'm doing it with one hand. I'm looking away, just in case it blows up. This stuff does blow up. I don't know how I'm going to light something on fire because 120 volts will blow up when you, you know, short it out. So I'm still figuring that out. Anyway, so here's my low level float switch. I'm going to put a little bit lower than the original high level one. Just a little bit. We want it to be low enough that there's a noticeable difference for our process. Let's see what happens. All right, so I'm going to dump. Put it down there. Dump. All right. Low level should be made. High level should be made. Yeah. See here, we'll do it again. Stand by, I'm going to get a little more water. Really show you the process. And I'm going to move the camera because you guys don't need to see me. You just want to see the process. So I put the high level switch up a little higher. We're going to actuate the low level right there. And the high level should come on. Come on. Rinse and repeat. There's your float switch controlled lift station, pumping station. Let me turn this up. Hopefully you guys can see me pretty good. Obviously the floats are going to fail. Things are going to fail. So a lot of times you'll have alarm monitoring. Good way to produce an alarm for a system like this. Say you don't want your tank to overflow. What you would do is you would put another float in there. You call it your high alarm float. Make it higher than the rest of them. You know, and that will let you know that either, you know, the float process isn't working or maybe your pump stopped working. And you can use that high level float to either, you know, turn on a buzzer or maybe, you know, if you're connected to a PLC, it can, you know, send an alert somewhere. And generally for like a high alarm like that, what you would do is you'd actually run a normally closed circuit. Anything that, you know, is an alarm or a safety feature, you want to always have power. And then when you lose that power on that, then, you know, that's when you want to send the alert. So, you know, if it fails, you want to get the alarm. So you can put a high level float normally closed. You can also use that high level float tied to a timer, you know, a timer off, an off timer. So when you get that high level float, maybe you automatically turn on the station for, you know, a minute just to keep it manageable until someone answers the alarm. This is what you would use to operate, you know, a cheaper pumping station where you want to control the level. Float switches are pretty common in industry. A lot of times we use 3-phase motors instead of single-phase motors. They're just more robust. So in that situation, instead of using a relay to power your pump, you would use a contactor or a starter. Fuses are pretty common. Starters have overloads on them. So if a motor fails electrically, or if the pump gets clogged up and it can't move, or maybe you blow one fuse and you're single phasing, the amperage is going to shoot up, and higher amperage means more heat. Those overload units will actually heat up, and they will pop open. Your overload will trip. If the overload fails, then your fuse will pop. If your fuse fails, then your circuit breaker will pop. So generally in industry, you'll basically see that same exact schematic over and over again. You see it in motor controls. You see it in this stuff. Again, that's for more rudimentary systems. You can start getting into multi-million-dollar systems, things that are, using a $100,000 motor. Then at that point, you're going to see things like variable frequency drives, level sensors. Say this pumping station uses a $50,000 pump, and we don't want to turn it on and off. We want to reduce the number of times we turn it on and off. Maybe we have a level sensor that gives us an exact level, and then that will be converted through a PID controller to a speed output, and we'll control the speed. And rather than turning it on and off, maybe we'll just keep the level right around, a certain area, so we can, control the number of startups. When you use a variable frequency drive, it's just a controller that controls a pump's speed, how strongly it's pumping, or a motor rather, it controls a motor's speed or frequency. So we use that with more expensive motors to make them last longer. Rather than starting them up at 100%, turning them off all the time, we can slowly ramp up. And if we want to, we can control the number of times we're turning it on and off throughout the year, and it will extend the life. It's all just like, it all depends on how expensive your process is, and how much it costs to fix. There's a lot that goes into it. There's a little bit of, some explanations of how things work. In this system, we're pretty much just using float switches. We could generate that signal to turn on. You could have a selector switch, and maybe you put it into manual mode or automatic mode. Maybe you have a PLC discrete output. That's the first step. That discrete output energizes your circuit. Yeah, so that's just a little bit of that stuff. I hope you guys enjoyed it. Just sharing you what an electrical technician does, what we look at. Hopefully you learned something. If you're a new technician, definitely check out my other videos. Instrumentation, automation, electrical technician stuff. I enjoy what I do, and I love making these videos. I hope you guys enjoyed it. Have a good day.